Okay. Let's start our lecture number 6. And now we are going to start to study electrostatics in material media. And the plan for today we are going to talk about, initially we are going to study the behavior of the field produced by an electric dipole, because that's a seed for insulating material. Okay? That's a constituent basic element, let's say. For an insulator, we have atoms or molecules that are neutral in principle, right? Uncharged. But you can either have spatial separation of charges, either naturally or by an external field. And if you have separation of charges, if that is ordered separation of charges of the different atoms, you might have an external effect, a macroscopic effect. So then you have some alteration in the field, in the total field, because that's different than applying field in vacuum, no matter, right? Have a material, have different atoms, you separate charges, then they in turn produce an electric effect, then you have to sum those effects. So that's why it's important to start with electric dipole. Obviously, there are other low-order contributions for insulating systems, insulated systems. We can have 4 charges that combine to have a 0 net charge, right? We can have a quadrupole, for instance, right? So we can have other higher order configurations or combination of neutral systems, combination of charges that form neutral systems. You can have a quadrupole moment, for instance. But for us, it will be enough to study the electric dipole to explaining insulating materials. Okay, so then we are going to make a generalized definition. I mean, we're going to conceptualize it like the dipole as a very simple system, model system, pair of charges. Then we go on to generalize the definition. Next, we will define what is a polarization, a polarized material, what kind of quantity is representative of that polarization state. And then we will finally derive the constitutive relationship between fields in a material media, insulator. We are going also to study conductors, so we're going to have another constitutive relation, but we'll see at the end of this course that we can put all the properties, at least electrical properties, together in a single constitutive relation that's concentrated in the permittivity of the material for linear materials. So we'll see that these things they are easily interpreted after we have all the quantities well defined and well understood. And finally, when you have obtained the constitutive relations, then we will be in a position to have the final form of Maxwell's equations in material media. And we will do some simple, classification of different types of dielectrics that we find on an everyday basis. Reference for this lecture We have the ebook chapter 2 and Jackson chapter 4. Okay. In fact, Jackson talks about multiple fields, but he has he dedicates some part of the book on the dipole properties. So let's consider, for instance, initially a simple model in which you can look at this as an isolated system. Okay. You see those things. You have a pair of charges. You have a pair of charges, Q and minus Q. Okay. They are separated by a distance d. And we can calculate the electric effect due to this separation. I mean, the total charge is 0, right? But we can calculate the effect, how the electric effect depends on the charge magnitude and the separation distance. Okay, this can be called an electric dipole. Dipole because there are two poles, one positive and one negative, and we can have atoms or molecules that are, formed with the different with the separation between charge centers. That's why we call it a electric dipole. So what we want to do is to calculate the effect at point x. In spherical coordinates, this point x makes an angle theta with the z-axis. So why is this important? If you look at insulating materials, right? The main electric effect that we have in insulating materials is that due to charge separation, right? I mean, for instance, let's make the very simplified assumption in which you have a spherical symmetrical atom, let's say, in the absence of an applied field. So you see that you have electronic clouds around the center, right? You have a center here, the nucleus, the positive charge, and have electronic cloud around, right? What happens when you apply an E field? Well, you just simply push away the positive charge, right? And you pull the negative charge. So you make a separation between charge centers. So you create a dipole, right? So the effect at point x is can be easily calculated, right? Is the potential. I mean, first we start to determine the field. For instance, we start determining the potential function. It's going to be the contribution of the positive charge, and that due to the negative charge. Let's say that the positive charge is located, right? I'm just going to draw separately here. I'm going to this is x plus. The negative charge is at vector x minus, right? So the distance between positive charge and point is the difference vector between x minus x plus. And for the negative charge, it's going to be x minus x minus. So it would be this vector here, right? X plus, x minus. So it's simple to calculate the potential, right? Due to the positive charge plus that due to the negative charge. This difference vector is simply plus or minus d over 2 times the AZ versor, right? So we are interested, I mean, if we are talking, of course we can calculate very close to this system, to the origin of the system. But if you're talking about atoms, okay, we want to consider the situation in which the distance to the point P is much larger than the separation. We want to see the asymptotic behavior. In fact, we want to determine what's a point dipole, right? We have a point charge, right? Point charge. We have any system of any size far away from distribution becomes a point charge. The potential goes with the distance, right? Inverse of the distance in vacuum. Now I have a point dipole, right? Very far away. The question is this: how is the potential? How does it depend on this point dipole? Okay, instead of a point charge, right? Point charge, we know the behavior. So far away from a point dipole, what's the behavior? So what we're going to do is that the distance much larger than the separation distance, then we can make an approximation. We're going to use that property of the nabla operator. We can expand a function f of x plus a small vector delta x approximately f of x plus the first order correction is delta x, which is the shift, right, in position, dot the 3D derivative, which is the nabla function, right, nabla of f. It's calculated at x, right, assuming that delta x is 0. So the same thing, you're going to have x minus x plus minus to the minus 1. This is the denominator here, right? So we have that inverse function here. Okay? This is approximately the function. This is the correction delta x. No, not this, I mean, in fact, you see here, right? So this is approximately the function at x, which is x to the minus 1, okay? Plus the correction, delta x, which is minus x plus minus. Here, if I put the minus here, right? No, this is right, okay. Yeah, I would, if I put the minus there, it would be minus, so I just made it here. I just put it here, okay? So, dot gradient of the inverse function. So this is x to the minus 1 minus x plus minus. The nabla of the inverse function, we saw that earlier, I mean in the previous class, previous lectures, minus x divided by x cubed magnitude. Right? So that's what we have. 1 over x minus the correction, which is x plus minus, dot x divided by x cubed. So use that, and then when we do that, and when we combine those two terms, okay, that's the result we just got. We obtain, just do some small calculation, quick calculation, you're going to have that the potential the asymptotic behavior is like this. You have the difference vector between the two charges. You have the position x, you have the cube of the magnitude of x. And then we define this parameter. This is a vector, right? So this vector we call P, which is, this difference here is simply DAZ, right? So this is called the dipole moment. Right. Some right here. Dipole moments of this isolated system of two charges. Dipole moment. So if we, so it means that in fact the effect, how high is the effect depends on this product essentially, QD, right? And also the effect also has some directional dependence. Depends on the angle between x and the angle and this vector here. Between those two vectors, the angle between x and P, right? I have to determine, depends on that angle. If it might be affected by that angle, and also by the magnitude of this vector. Okay? So that's the final asymptotic behavior of a pair of charges. So the potential has this dependence. And let's see what does this formula tells us. Well, the first one is that the magnitude of this thing here is 1 over r squared. So potential of a dipole falls off as 1 over r squared. Right? First observation. First remark. Second, the potential also is proportional to the magnitude of the dipole moment. And finally, the directional dependence. Potential depends on the cosine of the angle, right, between the dipole and the position vector. So let's just review this. Just see this here in this illustration here. For the monopole, as I mentioned, potential is spherical symmetrical, right? Doesn't depend on angle, just distance. 1 over r is the dependence, and the intensity of the effect is proportional to the charge. It's a zero order moment, is a charge, a monopole, okay? So we have here monopole. Monopole is always when the potential goes with 1 over r. The dipole is weaker, the effect is weaker. So if you express here x in spherical coordinates, you're going to have here RAR divided by r cubed. So you're going to cancel that out. You're going to have r squared. So that's what we're going to have. We're going to end with this expression here. So it's a dot product between P and the directional vector, which is the radial versor, divided by r squared. Right? So now I have the dependence on two parameters, angle and distance. Also, monopole is 1 over r, dipole is 1 over r squared. This is a characteristic dependence. So every student in electrical engineering, even more, I mean, every master or PhD student in electrical engineering, okay, has to know by heart that the potential of a monopole goes with 1 over r, and for a dipole it has to go with 1 over r squared, the point dipole, right? So it's very important to do that. Now we can calculate the E field by simply applying the connection with the potential, which is minus nabla, minus gradient of potential, right? So just recalling that the nabla, we are going to apply nabla on that expression. That's what formally, that's what we are going to do. We're going to apply nabla, which in spherical coordinates is AR DDR, right? Plus H theta over R, derivative operator relative to theta, and A phi sine theta is the phi, right? Then we want to apply essentially potential is, let's say like this, 4 pi epsilon 0 times potential equals to P dot AR over R squared. Right? So in each case, I'm going to apply this derivative on this system here. Okay. So let's make here very detailed just to show how it is. DDR of P dot AR over R squared. Well, this factor here doesn't depend on R. It goes out of the derivative. So there's a total derivative of the 1 over R squared. Okay, I'm not going to calculate, I'm going to outline. Okay, this is somewhat summarized in the class notes. I'm just going to show you separately here. So the second term is 1 over R dd theta P AR over R squared, right? So here in this case, R squared is out. It's 1 over R cubed. So I have, now this thing here depends on theta, so let's just make a total derivative of a product of two terms. So that's 1 over R cubed. So here, this element here is constant, right? This is constant. So this is going to be P dot DAR d theta. We have done that before. I hope you guys have done that in your homework assignments. This is the derivative of AR, which is A theta. Right? So the first term we are going to have, first term is this one here. I didn't calculate, but this was minus 2 PAR over R cubed, right? The derivative of R to the minus 2 is minus 2 R to the minus 3. So this one factor, the other is this one. And then we have the third one. I'll leave it to you. Okay. So is outlined here, right? Those calculations. In fact, I mean, if you work this out, I can if you work this one out, this one, right? This one is just, this one is P cosine theta. You can formally make the derivative of this term, or just knowing that it's P cosine theta, then I know that the derivative relative to phi equals 0. So that's what we got, right? We have this thing here. So we have a third power dependence of the A field on the denominator. And we have this combination of terms. We can add and subtract P, you can add P dot AR. You can add this and subtract. So you're going to end up with 3. And there's going to be a term which is going to be, when you subtract, right? You have, just notice that we have this factor here. So we're going to have minus P dot AR plus P dot A theta, A theta. So that's what happened. I summed PAR, and subtracted. So we were left with this additional term here. Let me just work this out. Equals to minus, right? Minus PA theta. Is this right? I think there's some wrong sign here. Let me just a second. Let me see my notes here. Just a second. Oh, there's something wrong here, okay? This is supposed to be, just fix that in your class note. This is supposed to be minus here. Because we have this minus sign here. So just continuing, we have a minus sign that comes from here in front of this term here. So the derivative here was minus, with minus is plus, right? And the derivative here was plus, so we have a minus here. So this is this minus there. So please fix that in the class note. I hope I can remember to fix myself, to fix the class note myself too. So when you do that, so I was doing that calculation, right? So we had, in fact, what we had was this. I subtracted this term, and we have that one. So those two combine as this, as plus PA theta, A theta, which is the most important part here. So that's the decomposition of P in terms of the spherical system, okay? That's P, that's the angle, that's AR, and that's 90 degrees here. That's A theta. So the composition of P in the spherical system, P doesn't have an azimuthal contribution, only a component, only one radial and one polar component. So P dot AR is cosine theta, right? So that's one component of P, in fact. That is one. The other one is P dot a theta times a theta. So this is nothing less than P itself, right? So that's what we get. So that's what we have here. 3PAR AR minus P. That's, let's say, a canonical way of expressing the E field. Is easy to remember. So it goes with the third power of R, 1 over R cubed, right? And we have this this factor there, okay? Well, we did that just for a simple pair of charges, but let's do that for a more general form of charge distribution. Let's make a generalized definition now for the dipole moment. I mean, whatever is your distribution, let's say you have a localized distribution of charge, right? So there you have a localized distribution. Means that I can always find a sphere of a given radius A that always encloses all elements of the distribution. This is in principle a neutral system with the charge density rho, okay? So we want to measure the effect of this localized distribution at a distance, at a point in space represented by vector x. So we're going to talk about the asymptotic regime, right? So the potential is given by that standard integral expression, right? And then again, we're going to make an approximation. In the asymptotic case, we want to study the effect when x, the magnitude, is much larger than the size of, much larger than A, right? So that's what we want. I mean, x is much larger than A, which encloses the distribution. So x prime is always has a magnitude that is smaller or equals to A. So once again, we are going to make that expansion of this inverse function, right? Is equals to the zero order term plus the correction. So we have the number of inverse function. Again, we're going to have the same thing that we just did, okay? As the gradient of the inverse function has a minus sign, this minus sign is going to cancel this one. Is going to be positive here. So we have first term and that term there. So what happens if we plug that in the integral expression? So this thing here, the inverse function is going to equal. I'm going to make it like this: 1 over this thing here. It equals to 1 over x plus x prime, or differently, x dot x prime over x cubed. So notice that this thing goes out of the integral, can be taken out. The same thing for this term here, right? So the only thing I cannot take out of the integral is x prime. Right. So what happens that one integral is going to be on this term divided by x, which is the standard monopole effect. If you have some monopole, some net charge, is going to give a monopole charge contribution, which is the total charge of the system divided by the distance. The second term is a cube, right? So we have a third power dependence on the denominator, but we have a first power depends on the numerator, so we have 1 over distance square. So what we have is the x in the numerator and x cubed in the denominator, and p is an integral, right? That's what is left, is simply the integral of this factor here times that. This has been taken out of the integral already, it was already approximated, so and the rho is going to be at play here. So that's what we have, right? The monopole term is this one, is the integral of the charge density, and the dipole term is this one here, right? So you see that is the moment of the charge. Charge is this dq, right? So you can see that the dipole moment is as if I was calculating, if I were calculating this type of thing, a moment of charge, right? Charge located at dv prime, at x prime, so that's what it is. Moment of charge. So we have some moment, some vector. Dipole moment is a vector. I didn't mention, but it's easy to infer that is Coulomb times meter, right? So if you have an if you have an electrically neutral system having charge density rho, but the system is neutral, so Q equals 0. So the lowest order contribution is that due to the dipole term. Okay. Of course, as I mentioned to you before, there are higher order terms with much lower strength. Sometimes the dipole term has a 0 effect, so we have to look for the next order contribution, the quadrupole effect. Okay, so that's why you have to pay attention to that. In certain very specific situation, people from nuclear physics, they take that into account, right? So let's make some examples of calculation of the electric dipole, okay, of some systems, some hybrid systems, some discrete systems, some continuous mixed with discrete. So let's see what happens. Suppose you have, well, let's see what's the dipole moment of the system, right? So let's talk about the density. Let's use the formula. Dipole moment formula is this one, right? It's the integral over the distribution of the product x prime times rho. So in our case now, rho of x is the combination of two delta functions, one that picks up at d over 2az, which is the location of this positive charge, and the other one picks up at minus d over 2az. So that's what is the density in terms of delta functions, right? So applying the definition, we are going to integrate this times x. So we have two integrals. One involves this delta function. So I have the first integral. And the other has a minus q involve the other delta function. Oh, no, of course, the integral of any function that's multiplied by a delta function is going to be the function calculated at the singularity point of the delta function. In this case, this is going to be x equals to d over 2az. The other one is going to be x equals to minus t over 2az, d over 2az. So this minus is going to be canceling this minus here. So you're going to have a sum of two terms, qd over 2 twice. And then we have what we mentioned, before, right? The dipole moment is simply the product of the one charge, the positive charge, times the separation. And let's always recall, the electric dipole moment is always directed from the minus to the plus centers of charges, right? Or to the minus, to the negative charge to the positive charge, or to the center of charge negative to that of the positive center of charge. Let's make a second example. Let's talk about a neutral system. In fact, this example is a set of discrete charges, okay, forming a neutral system. And also, the center, let's position the center of charge at x0. The center of the volume that we're talking about is x0, whatever x0 is, okay? And then we have the location of the nth charge, which is xn, right? So let's assume the system is neutral, right? Sum of charge equals 0. Let's make case 1 x0 equals 0. So the origin, I put x0 equals 0. So let's see what happens if we do that. Well, if we do that, we just apply the definition, right? So we're going to have several delta functions, right? I didn't write, but the density equals to sum in any charges of Qn delta x minus xn, right? That's what the density is. So we just put that thing here. So that's why we have this sum, have this integral, and as we are picking up the whole volume, picking up the integration includes all the charges. So this is going to be x equals to xn. So that's the dipole moment. If you have a set of discrete charges, you can calculate the dipole moment by this formula here, right? Well, let's now assume that we have displaced the origin of the system. So x0 is not 0, okay? So now, here we have to change to x0 plus xn, right? So instead of xn here, we are going to have now this vector. We can separate in two terms, right? One that has the x0, the other has the xn, as before. Okay. Well, this is the same dipole moment I just calculated in the previous example, right? And this is the sum, right? This factor here, we can factor out x0 from the sum. I'm going to have a sum of all the charges, which is going to be equals to 0 because the system is neutral, right? Of course, if the system was not neutral, you would have a contribution of a monopole term that would be included, right? So we would have a monopole term, we isolate that term, then the remaining part, which gives the total charge equals 0, would yield the dipole contribution, which is that sums of those terms like the one I just showed you, okay? So the third example I'd like to show you is that, for instance, suppose I have a hydrogen atom that we apply the field and we separate, you don't distort. Let's assume that the atom has a spherical electronic cloud, okay? You just display the center of charge. You just push away the positive charge and you pull down the negative charge. So what is the induced dipole, right? let's make this example here. Let's assume that the density of the charge, let's assume that we have an electronic cloud like this. I just separate the charge by externally, so the positive charge is separated, is above, okay, and then a negative charge is below, and I'm putting here the reference on the center of the sphere, okay. Origin is at the center of the sphere. So it means that the positive charge is displaced by an amount, by a distance d from the center of the sphere. So now we have a density that can be written in this form. So it's a uniform. Let's assume that the cloud is uniformly distributed on the sphere. So we have the rho 0 density, and the density associated to the point charge, which is the nucleus, let's say. It's a localized system, okay? And the density of the electronic cloud is uniform, so it's the total charge is minus q divided by the volume of the sphere, 4/3 of pi a cubed. So applying the definition, right? What happens? So we're going to have one factor is going to be rho 0 times x, right? Integral of this. The other is going to be this one times x. And we know, which is this factor here. Well, rho 0 goes out of the integral. And we have x. This is the average value of the x vector in spherical coordinates. That's going to be 0 because the average value of the x vector is the origin of the sphere. You can calculate that by decomposing x in spherical coordinates, doing yourself the calculation, okay? But it's easy to demonstrate by these arguments that the value is 0. And the other one is going to be simply q daz. So the dipole moment is q daz. What is that? It's the distance between charge centers. The positive charge center is in the nucleus, and the negative charge center of the clouds is at the center of the sphere. So it's simply, effectively, we have separation of the charge centers. That's how you calculate. So, I mean, it's important to understand very well the general definition of the dipole moment. So you can calculate for a molecule, have different charge centers. We can calculate where is going to be the resulting dipole moment. You have a cloud around. If you can model that by a function, a wave function, we can obviously calculate the dipole moment, right? So that's all we have to do, all we have to discuss relative to the dipole moment. Now we are going to assemble several point dipoles. We're going to form a material. The material is an insulated material. I mean, we know the contribution of the monopole, right? We are interested in the contribution of things that are neutral, but we have some state of separation. We are going to talk about polarization of a material. When we talk about polarization, it's because we're saying that for some reason we have ordered, or not, I mean, it depends on how it's done. But we have separated the charges of the constituents of the material, either by an application of an external field, or because they interact. I mean, you have permanent dipoles, right? You can have permanent dipoles. Some other molecule has a permanent dipole, with separation of hydrogen. Then we have they have oxygen. Then have two hydrogen atoms. The centers, the positive charge and the negative charge, have separated centers, have centers that are separated, right? So I have hydrogen here, and the center of the, let's put well, not going. I'm going to put just a positive nucleus. You just say that's oxygen there, right? And we have an electronic cloud that's something like this, like a boomerang, right? So we have effectively we have a separation of charges. Okay, so we have some dipole here. You have to calculate. I mean, it depends on the angle of these things here. Depends on several factors, right? So we have a separation of charges, electronic cloud, and positive nuclei, and we can calculate that. So, and again, we're going to assume a microscopic volume that has a large amount, a large number of point dipoles, in which we can consider that the dipoles are continuously distributed on the volume. Okay, so we're going to say that in a volume dV prime, we have total dipole moment dP, and we are going to define a density function that allows me to calculate dP from the volume dV prime. So that function is the function capital P, which is a vector. This vector is collinear, right, with the dipole moment vector, the local dipole moment vector. So now if you have a dipole located at x prime, all we have to do is to shift the reference, right? I mean, have a dipole here, dP. Let's say that's x prime is the location. The effect is at x, right? I mean, all I have to do is to shift my origin to x prime. So the potential due to that dipole is dP dot this difference vector right? You are being blue here, but it's okay. 4 pi epsilon 0 x minus s pi cubed. So in our case, we are talking about the total dipole moment in a volume, which is given by this function here, p dv prime. Okay, so this function, the polarization, is simply the ratio dp dv prime is measured in coulomb meter by cubic meter, which is coulomb per square meter. It's just like surface charge density units, coulomb per square meter, right? So if we sum up all the contribution, you make that change of variables. You're going to have here P of calculated x prime dv prime. Then we're going to sum all of these things. You're going to have this result. The potential now can be calculated for a collection of dipoles. So I can calculate the electrical effect of insulated materials if they have a state of polarization, right? If I know that state of polarization, I can calculate the effects. Okay. So that's I mean, I can do some calculations here. For instance, let's assume that we have a material that attained a permanent polarization state. Just like ferromagnetic materials, we have those so-called ferroelectric materials in which you can apply a field and you can align all the dipoles, right? You apply the field, external field, have several dipoles that are misaligned. So those are already permanent dipoles, right? Dipoles have a permanent momentum, but permanent dipole moment, but they are randomly aligned. But the total dipole in a volume is effectively 0. So have a material like this. Then you apply a field, and we know that this tends to align. I'm going to talk about that energy, right? Interaction energy. In fact, I think I skipped that thing. I should talk about that. I'm going to just do this example and just to talk about the energy of interaction, okay? I'm going to come back to that later, but I mean, I like to talk about that too. So the tendency is this dipole to align in the field. So after apply a field, we're going to have some ordered, you know, situation. And when you remove the fields, the internal interaction is so strong that they keep aligned. So you create a state of permanent polarization. So certain materials, ferroelectric materials, have this property. So you're going after we remove, you have E equals 0 and P different than 0. Okay? Even if you remove the field, the polarization remains. So we're talking about this. So let's make an example of such a material. So have a small plate, circular plate, very thin thickness, right? And let's calculate the potential in the z-axis, right there. So the polarization is given, it's constant to the z direction, right? So you can look at the dipole moment of this plate, of the circular plate. Simply the integral of P dV. P is constant, it's just the volume times the constant P0. So it's like I mean, if you can calculate the effect of this disk far away from the disk, it's going to be that of a dipole of dipole moment P given by that, which is a canonical expression, right? The asymptotic expression. So the potential far away from the disk is going to be something like this. P given by this volume times the polarization. We can see how, I mean, you can calculate that. I mean, I'm doing some calculation. You just make some reference to the calculation we are going to do now. Let's express this into the angle and the, you know, and the polarization, which is here. So it's going to be P0 a squared T times cosine theta over R squared and 4 epsilon 0, because we have a pi that canceled out here, right? So we have in the plus z axis, okay, so on the plus z axis and on the minus z axis we have those expressions. So on the plus z axis, cosine theta equals to plus 1. So we have this result here. And the minus z-axis, cosine theta equals to minus 1. And also the distance is on the z-axis. So this is, so on the z-axis, r equals magnitude of z, because it can be positive or negative. So it's going to be something like that. All right. So that's the asymptotic result, right? We have the expressions here. Well, let's calculate exactly the potential on the z-axis, we are going to have tools to calculate off the z-axis to this expression, okay? But now we don't have those tools yet. Those special functions that we are going to discuss in this course. So to calculate the potential, let me just do it separately here, just outline the calculation here. Let's write down the expression. The potential at point X equals to dV prime polarization function dot product x minus x prime divided by 4 pi epsilon 0 magnitude cubed, right? Now, what we have to do in this expression, every time we do an integral like this, we have to know what is x. In our case, is the location where you calculate or you observe the effect, ZAZ. We have to know what dV prime is. In cylindrical coordinates, I mean, because the thickness is already fixed, this is a very thin slab, we are not going to do any integration in the z direction. We're going to assume that everything is in the plane z equals 0. So we're going to just put the dz equals t, okay? So we have now the remaining part of the volume element is r prime dr prime d phi prime. That's the second thing that we have to know. And also the location x prime, right? Let's look at the disk. We have x and y. This is the area of the volume element, which is here. That's the location. X prime is this one here. I'm not going to write it. This is the angle phi. The distance is r prime. Okay, so x prime is r prime. A r prime. Remember that this is a versor that changes as you scan on the surface. You scan x prime on the surface, right? So you see that, I mean, you can do some external calculation here. This thing here, which is x, I'm going to calculate x minus x prime square, which is magnitude of x square plus magnitude of x prime square minus 2 times x prime dot, right? So this equals to x square is z square, right? X prime square is magnitude of this vector minus 2 dot product between those two elements here. 2z r prime oh, I'm sorry. They are orthogonal, right? I don't have to do that. So that's what it is. There's no AZ and AR are orthogonal. So that's what it is. So x minus x prime cubed equals to, we have to raise this to 1/2 and raise again to the 3rd power. So it's going to be, I'm going to do it like this, r square plus z square to the 3/2, right? So we have that. So that's the type of integral we have, right? So just putting everything here. So I already separated the phi integral here. I have the RDR element, the P0 AZ dot x minus x prime, the magnitude down in the denominator, right? So you have, this is going to be 2 pi, with 4 pi, you have 2, right? And here we're going to have a very messy thing here. I mean, this is going to be P0z. This dot product here is 0, right? So I can remove this P0z from the integral, so it goes out here, P0 and z. So we have I mean, this dot product cancels with that one, right? So we essentially have P0z is out, so we have an integral of r prime dr prime divided by z square plus r prime square through the 3/2. So, so this is easy to calculate because you have a function, have the derivative here, right there, unless of a factor of 2, right? So, so this is going to be essentially this integral here. Let's do something like this. Minus 3/2 r prime dr prime. If I call this u, this is going to be du over 2. So it's u 1/2 u to the minus 3/2 du. I want to calculate the integral because, and again, I'm going to have some important suddenness on this integral here. So this integral is going to be 1/2 of u to the minus 1/2 divided by minus 1/2. So it's minus u to the minus 1/2. Okay? So this is going to be, I'm going to invert the limits. This is from lower limits, which is r equals 0. This is from z square to a square plus z square. So I'm going to invert the limit. It's going to be u to 1/2 from a square plus z square, u to the minus 1/2 to the z square. So this is going to give, I'm going to go up here. It's going to be equals to 1 over z squared to 1/2, that we have to be careful, right? Minus 1 over a square plus z square to 1/2. So here we have to be careful because we have to extract the positive root. Okay, because there's no, I mean, you cannot change the sign of things. You have to be careful there. So this is going to be 1 over magnitude of z. That's the detail you have to pay attention, okay? So when we do that, that's why we have this term here. And the second term of the integral is right there. Okay? So there are some important details. For instance, if you calculate on the top of the disk, z equals plus t over 2, and you calculate the potential at the lower part of the disk, minus t over 2. Let's call those things phi plus and phi minus. So the potential difference, phi plus minus phi minus, is simply this term here. It's polarization times thickness divided by epsilon naught. Okay. So also we can do an asymptotic expansion. Let's assume z much larger than a. Again, we use a first order approximation. We can do that, right? So the zero order term is 1 over square root of z squared, which is 1 over magnitude of z. There's a correction there, right? Then we can, I'll leave that for you to work this out, okay? There's a term which is going to cancel. The term that would be a monopole term. There's no monopole here, right? And we have this term that is left, which is the third power of z. Notice that magnitude of z, right, is exactly what we got. This is the expression that we got in the approximated value, in the asymptotic, before doing the example, right? I mean, you just did here. We have this result in the plus axis, plus, and this result in the minus axis, which is the same as this one here, right? So this is going to be plus P0 TA square over 4 epsilon 0 z cubed, something missing, z square, I'm sorry, z square for z larger than 0, and for z less than, smaller than 0 is going to be minus, magnitude of z is minus z, right? So it's going to be minus z2, so it's going to be minus P0 T A2 over 4 epsilon 0 z square for z negative, as we showed before, right? So this is the result we have. So so in summary, the insulated disk, which is polarized, has a net electric effect. If I put a charge nearby, it's going to be repelled or pulled towards the disk. One interesting concept when we deal with polarized media is that due to polarization charges. You know that effectively what happens is that when you separate charges in a macroscopic body, we have a collective effect that might result on residual charges on the boundary of the volume, okay? We can also have, if we have a non-homogeneous distribution of dipoles, you can have also polarization charges in the volume. Let's see how that happens, okay? So if you have the concomitant effect of free charges, we are going to make a distinction. Free charges are those charges that you can inject in the circuit and make it circulate between electrodes of a battery, for instance. Okay, I have a free charge, which is electrons, or electrons and holes in a semiconductor. You can have those free charges in a conductor, for instance, right? So we're going to separate the effect of the free charge. We're going to call those monopoles. So contribution of free charge is that due to a density rho free, rho f. So rho f is the free charge density. And also have bound charges. Bound charges are those that determine the dipole moment. So bound charges give a contribution that is represented by the polarization of the material. So we already showed that polarization gives a contribution that goes with 1 over distance square, which is this term here, right? So I'm going to play around with this factor here. So let's look at that. I mean, again, I'm going to face the nabla of the inverse function again, right? So let's look at that. So we have P dot difference vector divided by its magnitude cubed. So that's the same as nabla of the inverse function. Now notice that I'm using prime here. So I'm doing derivative relative to the x prime. So it's going to be plus, right? This is plus that. Okay? So notice by the chain rule that we have involving a vector and a function, that the nabla of a vector times a function, which is the inverse function here, equals to vector times nabla of the function plus, which goes there, right, to the first term here, plus function, which is 1 over x minus x prime, times divergent of p, which is the vector, right? So we are replacing, this term here by those two here. And recall that p is a vector that depends on x prime, so this derivative is directly on p, okay? So when we do that, what happens? We have one term that has a denominator which is the difference vector magnitude, which is the same denominator of the first volume integral. So you can combine those two. You can combine those two terms, right? And what we have left is this. So this goes to the first volume integral, so we have this one left isolated. So you see that this is the term that has a denominator, and the other is the divergent of this thing here, right? So here we have we can call this, you see that this is like an effective charge density, right? So it's rho f plus the sum, which is minus divergent of p. I'm going to call this an effective charge density, rho ef. And here we have Gauss's theorem. I'm going to transform this into a surface integral of this vector. Is the flux of this vector outwards of the volume that's bound by surface sigma. So you see that the volume is bound by surface sigma. So I'm going to transform the integral of the divergence of the vector in the volume through the flux of the vector outwards through sigma, right? So that's what we have. So in fact, we have the sigma. The differential vector is n, which points outwards the sigma, which is the magnitude of the sigma. So that's why we have this. You see that this sigma n is this vector here. So that's simply Gauss's theorem. So we end up with two contributions. So everything takes place as if we had a volume charge density that was obtained, rho effective, okay, plus the contribution on the boundary of the surface. That's the integral expression for potential, right? So so the volume charge density is that due to free charges and that to the bound charges. The bound charge contribution is simply minus divergent of P. So if P changes such that you have a divergence, then we have effectively is as if you had a volume charge density due to the bound charges, effectively, okay? And on the surface, the charge residue is given by this projection of P outwards along the normal direction to the surface. So it's as if you had some residual charge on the surface given by the projection of P over N, okay? Just to make a qualitative example, okay? First example, just qualitative, just to give you an idea. I mean, we can calculate things replacing the insulating material by its equivalent bound charges, volume and surface charges. So we can replace the material by the polarization charges in the volume and in the surface. Let's make a qualitative example here. Okay? Consider the thin plate or the thin disk, thickness T, right? We just did that before. This is T. Now we have, let's identify. You can solve the problem replacing the disk by its equivalent polarization charges, bound charges. So the first thing you see that we have a constant polarization. So the divergence of P minus, which is the volume bound, right? The charge density in volume is equals to 0 because this is constant, right? So there is no volume polarization charge. But if you go to the surface, we have to find what are the projections of the polarization along the normal direction that points outward the volume. Right? So if you go to the top surface, the normal is AZ, as P is aligned along the Z direction, so that there is a residue, right? A charge, surface charge density, which is P0 coulomb per square meter on the top surface of the disk, right? The same thing on the lower part. The normal outwards is N minus, which minus is minus AZ, so the contribution gives a minus P0 coulomb per square meter on the lower surface. So I have positive, let's say that P0 is positive, so I have positive charge on the top surface, negative charge on the lower surface, right? And on the, so we also have the surface, which is this surface here, right? On the side of the plate, the wall, right? The lateral surface. So we have the normal outwards L lateral surface, which is a R, which is orthogonal to P, so we have no contribution on the lateral surface of the disk. So effectively, you remove the plates and put two thin disks, two thin charge regions, and in between them you have vacuum. So effectively, this thing is equivalent to that. Remember the expression that we got, right? Everything takes place as if the distributions, the effective distributions, were in vacuum, right? Vacuum. Because epsilon 0 is the parameter that appears here. Here too, right? So it's a surface distribution in vacuum. Okay? So the plate is equivalent to two thin disks separated by a distance t, and you can calculate the field, or directly if you want, or the potential of a charge, disk that has a total charge, which is density times area, and the other one's density, which is negative, times area. So you can calculate, for instance, the field here in the middle, or anywhere in the space, right? Just replacing the disk by those two, the plate by those two thin disks in vacuum, right? Let's make another example. We are going to calculate this exactly in any point in space, but right now we are going to do use the equivalent charges, polarization charges, to calculate the problem of a sphere which is permanently polarized again, right? With a constant polarization vector. Let's align that. Let's align P along the z direction. We see that in this example again, we don't have volume polarization charge in the volume, right? Because P is constant. So this is 0. So we have only surface polarization charges, right? So you see that we have this term here because the dot product between P and the normal direction outwards the volume is simply you see this is going to be simply P0 AZ dot the normal, which is AR, and these vectors, they have an angle theta between them. So we have that function. So they have a variable surface density. So the charge density as a function of theta, right, is a cosine function. So the cosine is something like this, right? So this is rho BS. So that north pole, south pole equator here, right? So we have that. So you see that we're going to have positive charge on the north hemisphere, and negative charge on the south hemisphere. We have a maximum here, theta equals 0. In the equator, we have a transition of sign. So you're going to change, it's going to be 0 along the rim here, right? And then goes negative on this side here, going to a maximum negative value on the south pole, maximum positive in the north pole. So I have a continuous change of charge density. And have symmetry in the azimuthal direction. So we can calculate, we can replace the sphere by this equivalent charge distribution in vacuum. As a first we can calculate easily the field in the center of the sphere, for instance, okay? Because it's interesting, in the center of the sphere, the distance of any charged element to the center is always constant, right? It's always the magnitude of the magnitude is A, is the radius of the sphere. So we can calculate the field at the center of the sphere simply by using the integral expression for the E field. So it's going to be that dq x is the origin minus x prime, which is the vector that scans the surface, is AR prime, okay? And x minus x prime cubed, which is the denominator, is going to be 0. It's going to be a cubed. So that's what I have here, right? So that's what we end up with this double integral here, sine theta d theta, and the phi, and we have a cosine theta here, and we have the versor AR prime, which is a function, right, of theta prime and phi prime. So you have to be careful in calculating this. I'll leave this calculation to you to calculate this integral. So to do that, you have to decompose in rectangular coordinates. So we make explicit representation of AR prime in terms of the angular variable, so you can integrate, right? So the result you get is this one here. So the field at the center is directed downwards, and this minus P divided by 3 epsilon 0 is a very, very well-known result. We are going to calculate that in general. We're just calculating that in the origin, right? we are going to, in a couple of lectures, you're going to be able to calculate this in any place inside or outside of the sphere. So, and we will show that the field is the same everywhere inside of the sphere, right? So the field of a uniformly polarized sphere is uniform everywhere inside of the sphere. And outside, the field is exactly that due to a dipole placed at the center, with the dipole moment equals the dipole moment of the sphere, which is that one. We're going to show that. So these are exact field lines calculated using Mathematica. Inside, you see that the field is always constant. Outside, this is as if we had a dipole right in the middle here. I mean, those lines here, right? Those lines are exactly those of a dipole in the center. So a sphere is an exact model of a point dipole. Okay, the sphere gives exactly the coordinate dependence of the electric effect of a localized dipole. It's a good model, right? The exact model of that. Well, now after we have done this, we are ready to establish the constitutive relation in dielectrics. Constitutive relation is the relation between field quantities. Recall that so far, I mean, we are going back, we forgot vector D, right? We said before that D equals epsilon 0 E in vacuum, right? Now we forget vector D, we just did that temporarily, okay? Let's forget temporarily now vector D. So far I have two field quantities. One is due to the matter, and one is the field. Vector, I'm talking about the field vectors. Have an E field, and we have also now a new element that appeared, which is the polarization vector, right? So we have to have a connection between those two things here. Let's see what kind of connection we have. Okay. So when you look at the potential expression, right? I'm gonna write it down again here. Originally, when we didn't have polarization, we had vacuum, so we have a distribution of charges. If I wanted to separate volume and surface and linear contribution, I would make additional terms here, right? I could just do this, a simple integral, or I could separate them, for instance, a surface contribution plus integral over the surface, the sigma prime, rho s x prime. I could do that, right? But I could formally represent all the densities in the volume density here, right? Okay. So when we have that, when we have this thing here in the potential, I mean the equation, the differential equation for E field, the curl of E is 0, right? Because that hasn't changed yet. We don't have any reason to change that equation, because E is minus nabla minus gradient of phi, so it means that E is conservative. The curl of E is 0. The other one is, I mean, forget D, you don't have D anymore, we just have E. It's that divergent of epsilon 0 E, when you have a rho here, equals to rho. That's what we have. Every time we have a rho here in the volume integral, if we go to the volume integral, when you go to the divergent, the point, the differential representation of the divergence of epsilon 0 E is going to be the charge density. In other words, the element that appears in the numerator here. Okay? Now we have demonstrated, right, that when you have polarization, potential now is rho effective Well, I also had plus something on the surface if I want to. I can have a surface integral that includes the surface charge density due to bound charges, polarization charges, or even to free charges. We have to have free charges on the surface. We'd have a volume, a surface contribution, right? But also I can forget that integral and put everything in this volume density, right? And then I can make the particular calculation of the volume integral, reducing it to a surface integral if necessary, or to a line integral if the volume is just one-dimensional. I mean, this volume integral is going to be broken in different integrals if necessary. But in fact, what happens is that when you go to the differential equation, what appears in the second member of the divergence of the field is this factor on the volume integral. It's the effective charge density. So it means that now the equation, including polarizable media, is that divergent of epsilon 0 E equals to effective charge density. Okay? We have a change now. So it's whatever is in the numerator of this volume integral. Everything takes place as if this thing here was in vacuum, right? So now the equation has to be changed to this one, right? But what is this thing here? Well, this thing is this take into account all the charges now, free and bound charges, right? If we express, if we remember, right, that the effective charge density is the sum of the free charge volume density plus the bound charge density, which is minus divergent of P, we are going to drop that subscript. Now, every time we look at the rho, it's going to be the free charge density. Okay? So, what is free charge? Free charge is the typical charge that circulates in, that goes around in a circuit, electric circuit. Is moving charge, real moving charge, free to move. Okay, bound charges don't move. Okay, you have atoms; they are not. They cannot be accelerated on a field. They're going to just. All you can do is separate the charges. We cannot move that on a field, right? So we're going to have those. We're going to avoid carrying out. I mean, carrying in this subscript all the time. We're going to drop it. So we're going to have now this representation. So if we plug that in here, right, what we have, we can combine the divergence of P, can combine this with divergence of epsilon 0 E. We have the sum. So we're going to have something like this. And on the second member, on the right-hand side, we're going to have rho, which is the density of free charges, those that can move, right? So, and we call this new vector the electric flux density vector, or the electric displacement vector, D. So that's the real definition. So we have to introduce this vector to make a simple equation. I could just I could just keep using E and P in all the equations, but it's easier to interpret things if you do this, if you introduce this vector, the displacement vector. Has some interesting physical meaning too, right? Because of Gauss's law has to do with the free charges, right? So then we have divergence of D equals to the density of free charges. So when we have D here, we have free charges there, right? So this is called the constitutive relationship involving the vectors, the electrical field vector, which is electric field vector, which is D, electric flux density, E, electric field, and P, polarization. That's why it's called the constitutive relation in the dielectric, in the insulating material, right? So in summary, now we have concluded our formulation of the Maxwell's equations in electrostatics. These are the differential forms of Maxwell's equations. Now we have two vectors and a constitutive relationship. So we have to have two equations in two unknowns, which is D and E, but we have a constitutive relation relating those two things. So we have to solve this subject to this constitutive relation. And if you go to the integral theorems, we can go to the integral forms of this relationship. That's Gauss's law, okay? And this is the conservative property of the E field, okay? So curl of E equals 0 yields that the E field has 0 circulation. In Gauss's law, that says that the flux, electric flux, the net flux outside, that goes outside of a volume bound by a surface, equals to the net free charge inside of that volume, okay? So, so let's now just conclude the lecture briefly. We have some classification of dielectric media, which is typically employed. There are different sorts of materials with very interesting properties, right? But talking about the dielectric properties is essentially how D, E, and P relate themselves. Certain materials have allow it to simplify things. Those are the linear, homogeneous, and isotropic media, in which when you apply a field, we have a linear response, linear polarization. If you reduce the field to 0, the polarization goes to 0. So it means like this. When you increase the field, like this, the polarization increases. If you reduce the field, polarization reduces. The field goes to 0, polarization goes to 0. Field is positive, polarization is positive, aligned. Field is negative, polarization goes negative. So that's a traditional charge separation, dielectrics in which the field just produces charge separation, no orientation. Could be some orientation too, okay, some orientational effect. But if you have a material, insulating material, apply a field, effectively what you're doing is separating charges. So you have a response, which is a polarization. And if you reduce that field to 0, this center of charge go to the same point, and you don't have a polarization, you don't have a dipole, right? So many materials are like this. And also you can have materials that are made of liquid media, for instance. They might have polarized permanent dipoles, okay, but they are always randomly oriented. But when you apply a field, they orient with the field. When you remove, it's just a liquid medium, right? I mean, they just go back to be random again. So the polarization goes to 0. Apply a field, you have an orientation of the dipoles. If you remove, you go back. Okay. So I just wanted to talk about something that I didn't discuss, which is the energy of a dipole on a field. It's not very difficult to determine. I mean, suppose you have, let's make a very simple situation. We have two charges. We have here a system. You have a separation of charges. So here we have a x minus location relative to a reference frame. Here's the location of the plus charge. So I want to know what's the energy of this system, which is bound here by this thing here, right? Let's look at like an atom or dipole on a field. So you have, so this is immersed in a field. And this field is described by minus gradient of a potential function. So that's external to the system, okay? So the energy of the system here, let's call W, right? Because the energy of this charge on the potential, on its location, right? So it's minus Q. It's minus Q. Potential at x minus, and the other one is plus, right? Q. Potential of x plus. At x plus, right? So the energy of the system that is immersed on the field is Q x plus minus phi x plus minus phi x minus. So the potential difference between those 2 points. Well, if the separation between charges, let's call it D, right? Or D here is x plus minus x minus. If the separation between charges is very small relative to the scale of variation of the field, so I can approximate this, right? I can say that phi x plus is approximately phi x minus, right? Plus the correction, the famous term, which is shift x plus minus x minus, which is small, right? Dot the 3D derivative, which is the gradient of potential, where anywhere, okay, in between those two charges. For instance, can be in the middle here, can be at x minus. I mean, I can do that. That's not important. So it's number of phi in the system. The system is so small, but we can calculate the derivative in the middle, let's say, right? So it means that the difference is equals to this term here. So energy equals to Q x plus minus x minus dot nabla of phi. This equals to minus E. This equals to the dipole moment. So we have that the energy of interaction of dipole with field is minus P dot E, right? So what's the tendency if we have an E field applied to a dipole? Well, the tendency, if we have a dipole, the system has no relaxation effects, no losses, the tendency is the dipole to keep on the constant angle, right? Processing around the axis of the field. But I mean, every time, I mean, this dipole is not isolated. It interacts with other dipoles, other things, and it's going to relax. So the tendency is that the energy of the system is not going to increase. It has to go down. So the minimum energy occurs when this is maximum. I mean, it's minus the maximum value, and that happens when the P aligns with E. So that's why the tendency of any dipole is to align along the field, applied field. So that's why we talk about alignment, right? I mean, so in materials like those we are talking about, if you remove the field, alignment goes away. If you apply a field, everything aligns in the field. So I have a polarization that relates to the same direction of the applied field. So materials like this will have, can be, I mean, the properties, material properties of a dielectric like this, a linear dielectric, can be represented by electric susceptibility, right? And when you calculate D using the constitutive relation, so what happens? Well, if you use the susceptibility concept, so you have this combination is going to be epsilon 0, 1 plus chi E times Z. Observe that chi is adimensional, okay? So this is always a number. In general, for traditional dielectrics, the susceptibility is larger than 0. Okay, so this is called the epsilon equals to epsilon 0, 1 plus chi E. We call that the permittivity of the material, the electric permittivity. So here we have the simple relationship between D and E, right? I mean, we don't have to talk about polarization, just talk about the permittivity of the material. We have this simple relationship, linear relationship between D and E. Okay. So what happens? If we are in vacuum, the field of a point charge, the potential, you have those expressions, right? Q over 4 pi epsilon 0 r, and the vector is Q I R divided by 4 pi epsilon 0 r squared. If we immerse that charge in a dielectric with permittivity epsilon, right? Oops, things appear here. Sinking a little bit here. Okay. Then everything you have to do is to replace the vacuum permittivity by the material permittivity, like this. That's what you have to do. So it's very easy to do things in a, in a linear system. Also, if you go to the Maxwell's equations, it's important to consider that divergence of D equals to rho, right? So, in fact, if you look, I mean, there's no explicit dependence on epsilon here. So D would, for a point charge would be 4Q divided by 4 pi r squared. There's no epsilon appearing, right? Free charge Q, either in vacuum or under a medium having permittivity epsilon, will have the same value, right? But you have to be careful when you deal with the charge distributions immersed on dielectric media. If you go to Maxwell's equation, right, we have D here, and we have the free charge there, right? So if we replace that by epsilon E, there's a linear relationship. Now, if the medium is non-homogeneous, it means that epsilon is a function of the coordinates. Then I cannot remove this from the derivative here. Now, if you have a linear median and a homogeneous median, then epsilon can go out. Then you have those things that we just discussed, right? The divergence of E equals to rho. So in practice, this equation just says that we're going to do some examples in the next class, not today, okay? But if you have a charge density immersed in a medium having permittivity epsilon, the effect of the medium is to weaken the electric effect. I mean, the E field is going to be weaker by a factor which is epsilon over epsilon 0 weaker, right? Something like that. We have also materials that are non-linear, those polarizable dielectrics we just spoke earlier today, ferroelectric materials. They have the phenomenon of hysteresis. Okay, so if you polarize the material, you saturate, you align all the dipoles, as I mentioned before, and it gets to a point which you cannot increase the polarization any further. The only additional effect is additional separation. You can apply increasingly higher fields until you blow up the material, right? But let's say you stop it at a reasonable value, you're going to saturate, everybody's aligned. Then there's a second phenomenon. When you go back, you remove the field, you're going to have the internal interaction between dipoles, because one dipole produces field in the other one. So we have, again, internal interactions, and those dipoles may remain aligned. So at zero field, you have a non-zero polarization right there, right? So to totally remove the polarization, we have to revert the field to this point here. So I have to apply a negative field to make a zero polarization. And you enter into this cycle, a hysteresis cycle, you know. You keep entering this cycle here. You saturate again, so you don't have a single value response of the material. Right? So this is called a hysteresis loop. And now we have a nonlinear function and not single-valued function, because giving a value of field here, you have this solution, that solution, or that solution for P. The only way to know which one is the right one is to know where the polarization was sitting before. So we have to know the previous history. So these are nonlinear materials. And finally, just to quickly discuss this, we're not going to go over the detailed properties of materials. There's a subject, an entirely different subject area, solid state physics, right? So I'm just going to talk in general lines here. So it can have an isotropic dielectrics. In an isotropic medium, have a collinear vectors P and E, right? We have a scalar factor here. In an isotropic medium, well, the response depends on the direction of the applied field. So you can have a degree of response in one direction, which is different from the degree of response in the other directions, okay? So we have that. So in this case, we can have a linear relationship, but it's not scalar relation, but we have a matrix relationship. Now we have a susceptibility matrix, or tensor, if you want. These are tensors. In fact, they are classified as tensors because they have certain properties under coordinate transformations that put them in the group of tensors. So here is polarization represented as a column matrix, column vector, if you want. This is transposed, okay? So the relationship is a matrix like this. And what we have is that the relationship between D and E also is a 3 by 3 dielectric tensor, which can be written in this like this. This is the constant 1 in a matrix form for the dimension 3, right? 3 by 3. So I3 here is the matrix, identity matrix. So that's what we obtain, okay? That's the relationship between D and E is going to be a matrix relationship. And the same, the susceptibility tensor, or susceptibility matrix, which establishes the relationship between P and E. So that's about what we had to talk today, because we just concluded now Maxwell's equations in electrostatics with the presence of arbitrary insulating materials. So in any material, we have now the relationship between the differential equations and the integral equations that govern electrostatics. So we are going to stop here and see you in the next class. Bye-bye.